How to work with weak acids and weak bases to calculate pH. Which acids are weak? Weak acids are those that dissociate only partially. What does that mean? Let's take a general acid with its proton and the anion. When a weak acid dissociates, it does dissociate only partially. Some of the molecules of the acid that I put in the water will separate into the anion and the hydronium, but not all of them. So we establish this ice table just like we did in chemical equilibrium. And remember that the concentration of the acids and all the species here have to be in molarity only. So we establish the K of equilibrium, the constant, and you will see that if it's only one hydronium here and one anion here, the expression will be like this. Any weak acid with only one proton will have this type of K expression. Please see that the X here equals the concentration of hydroniums. You see here? So to calculate the pH, you should do minus logarithm of this X value here. In this expression, you can have different unknown values. If you know which acid you're working with, you know which K you will use because there are many tables listing the value of K for certain acids, weak acids. You know that the bigger the K, the stronger the acid is. Let's see the particular case of sulfuric acid. This is the formula of sulfuric acid, and you see it has two hydrogens. So why is sulfuric acid special? Because, for example, if I want to calculate the pH of a certain concentration of sulfuric acid, when you write the first equation, the first deprotonation, this equation represents a strong acid. The first proton of the sulfuric acid behaves like a strong acid. So the initial concentration of sulfuric acid will disappear completely at the end, and you will have the original concentration of the acid as the final concentration of the hydroniums in this first dissociation. But what happens in the second dissociation? This anion, it's called bisulfate. This anion behaves like a weak acid. You see that there's a value for Ka here in this table. So this reaction is an equilibrium. What is the initial state value of concentration for bisulfate? It's not 0, it's this value. And what's the initial value of the hydronium's concentration? This one. So when we establish the initial state, this is how it will look like. There isn't 0 for the hydroniums. It is 0 only for the sulfates. Here's the change. We respect the stoichiometric coefficients. In this case, it's all 1, 1, and 1. And at the end, we have this equilibrium state. So we write the expression for K, for the equilibrium constant, and we take the values from the last equilibrium state to replace all these values here, all these concentrations, in the expression of K. Working the math, we can calculate the value of X here, and finally we calculate the pH. How? It's not just this X value. Please see that the final concentration of hydroniums is the sum of this value, the initial concentration of the acid, plus the X we just calculated. So we have to do that sum and then calculate the pH with this total amount, concentration of hydroniums. So that's why this acid is special. The first reaction is strong, but the second is weak. What if we have to work with a weak base? The classical weak base in inorganic chemistry is ammonia. So if I'm asked to calculate the initial concentration of ammonia, I will have some other data, like the pH. In this case, it's 10. So we write the equation. Ammonia reacts with water, taking a proton from it and releasing hydroxyl ions. This is why ammonia is a base. Here is the value of Kb for ammonia. And we establish the initial state. I don't know which the initial concentration is, so I symbolize it like this. The change is all with ones, one ammonia, one ammonium, and one hydroxyl. And we have here the equilibrium state. Please note that X equals the concentration of hydroxyls. So we write the expression for the equilibrium constant and we replace with the equilibrium state data. Now, how much is X? I know that the pH is 10 because that's why the problem told me. If the pH is 10, pOH will be 4. And with the value of pOH, I can do the anti-logarithm and calculate X, which is this value here. So now we replace this value of X in the equilibrium constant, and the only unknown is the concentration. So here is how we solve this equation, and there it is, the initial concentration of ammonia. How do we calculate the K of a weak acid? For example, a solution of acetic acid, 0.1 molar, has a pH of 2.87. Calculate the K. We write the equation and we do the ice table. We know in this case which the concentration is at the beginning, 0.1. And we know the pH. So from the pH, we calculate the concentration of hydroniums. And we replace this concentration of hydroniums in X, like this. And we just do the math and calculate the K. So remember, working with weak acids or weak bases will only be just to calculate one unknown value from these expressions, this type of expressions, all right? You have basically three unknowns, the K, the concentration at the beginning, and the X. Knowing two of those, any two, you will calculate the third value. Thanks for watching. You know you can like the video. Please comment if you need further clarifications, if you have suggestions, subscribe.